So I would be continuing from here. So the topics which I would be covering are syntax, semantics, and design spaces, the characteristics of design knowledge, generic design, the role of prototypes, and knowledge-based systems. So optimization, it can be termed as making the best use of a situation using a set of variables. If you are for example, you're driving a car and at certain point when your speed is at the range of 25 to 30, you get an optimal economic sign. That means you're driving, your car is driving at a performance in which the mileage of the engine is optimal, or means at its peak under given circumstances. Another example would be a path optimization example, where you have a starting node and an end node where you have to reach, as well as the cost from one part to the another. So what you have to figure out is the route which you'll take so that the cost, which is sum of all the path distances. So you have to figure out a way in which you start from the start node and reach on the goal with the minimum amount, with the minimum number which you receive, the sum of these paths. So in this, the optimization variables can be the time, the distance, or the compulsory nodes to visit, depending upon the problem. But the problem with the optimization is that it can only deal with quantifiable parameters, which are represented in mathematical terms. So design descriptions are like the sentences in natural language where the performance of the design is not explicit. It's not mentioned how the design parameters would influence the performance of the design. It's just I want this end result. It's not that explicit. So the meaning is of the design description are derived from the interpretation of the design. If I have to design a car or maybe any other equipment, I am provided with a set of constraints and all those equations which I need to come up with. So the purpose of design is to find a description in the syntactic space which maps onto some intended space in the intended performance in the semantic space. So it's just giving it in a complex definition. So it means the same that the design in the syntactic space should be in the semantic space, which is if you're provided with the constraints and you have to come up with a design which optimizes all those constraints and provides you with the best performance which is achievable under certain circumstances. So the characteristics of a design knowledge. So it's more like a set of laws, rules, formulas, the materials which you can use, the objects, the space constraints, and the safety requirements. So it's it has different levels of sophistications, details, and abstraction depending on the requirements of the design and the areas in which the design is to be used. If you're designing an automobile or if you're designing a ship, the safety is of utmost importance, along with the materials used and the confinements of the different objects and the sensors and all those things. So the tasks which are difficult to model mathematically, it's some of the cases are there in which it's difficult to model a task in a mathematical form, but it's pretty easy to solve it using the knowledge-based systems. For example, that is one of the reasons why today machine learning and neural networks are gaining so much interest among people, because you don't have to write an explicit code every time for a specific problem. You can generalize the whole problem and you have the mathematical algorithms in which you can train the system so that it performs well on every specific problem. So it means that you have a generalized machine learning system which can perform well in specific domains. So one of the examples would be the Hamiltonian path. So the problem statement of a Hamiltonian path is you have to visit each node or the vertex of the graph exactly once. So if you try to formulate it in a mathematical format, it would end up quite complicated. But what happens if you just write a machine learning or a neural network for solving these kind of problems, it would turn out it's not that complicated. So even if I increase the number of nodes, if I add one more vertex over here, it won't be that much problem for the algorithm to work upon. But if you increase one more vertex, the mathematical complexity, if you come up to that, would increase tremendously. So it increases with the increasing in nodes. So this is like one of the examples in which the knowledge-based systems can really help you instead of like finding a mathematical formulation and then trying to optimize it. So the next topic is the generic designs. So generic designs are like a design space in a definition of a class of things where the class description is analogous to a generic model. Like if I define a car category like an SUV or sedan, it's just a generic design, like the SUV or sedan should have the minimum length, or it should have the engine capacity in this range. So it's like the general descriptions in which I can just place various car models into different classes. So it's like generic designs. One of the examples like of generic logos is over here. It's nothing special, they just came up with it. So it's simple, like you're using a normal word format and just using those designs. So the problem with these kind of designs is that if you show it to a client, he won't be able to connect to it. The connect with the product is missing. Like if I just take an example of ABC General Company, it's more like I'm not able to figure out what this company is actually focusing on just from the look of the design. Like we have the symbol of logo of Apple, so we know what Apple stands for, and like we have for the various car designers and all those things. So archetype is a certain design instance typifying a class, and the prototypes can be termed as a set of designs from which other designs can originate. So a role of prototype. So a prototype can be considered as an early sample, a model, or like a release of a product built on a concept or process, or to act as a thing to be replicated or learned from. So the thing is, with the prototyping, you usually get a feel of how the real device is going to work in, or how the real object or the real set of algorithms would actually work. So you can just improve upon them to increase the performance of it. So the purpose of prototype is generally to evaluate a new design to enhance precision by system analysis and users. So the prototyping serves to provide specifications from a real working system rather than a theoretical one. So it's like if you have a prototype of So if you have like a working prototype of a smartphone, it would be better as compared to a theoretical model. Like you have some theoretical formulations of the performance of the chip and the processors, but it would be better if you have it in a real device. So the sophistication of a design activity can be categorized in 3 levels. That is refining prototypes, adapting prototypes, and creating prototypes. So prototype refinement basically involves working within the class constraints of a particular class of designs. So what it actually means is, like if I take an example of a smartphone design, then I would be having the constraints of size, portability, communication standards, the battery capacity, screen size, and the durability. So it's basically it's like in choosing from a set of candidate designs with like I have a set of designs in which the size and portability are best, but the communication standards are below the market standards, or the battery capacity is high but it increases the size and reduces the portability. So I have to take into account every factor like size, portability, and the battery capacity, and try to optimize it so as to come with a design which is user friendly as well. I don't want to create a phone which has like tons of feature but it's not portable. It won't help anyone. Or like in the earlier days we used to have those Nokias, if you all remember. So you won't like to use it nowadays because you have the touch screens, and you would be using it. It's more comfortable. It's more user friendly. So in that manner, the prototype refinement can be understood in terms of product refinement as well. So also then the next step would be prototype adaptation. It just involves like extending the boundaries of a particular class of designs. So like the White Buzzer started with the experiments on the aircrafts, but currently, after the time and the technology, if you take into time and technology as well, you have the current A380, which is, I guess, the biggest commercial plane available right now. So it's like we started from trying to make a person fly, and we ended up with this. So the idea is basically we are extending the boundaries. So maybe in the next few years we might have the space travel possible. Like, we don't know. We still have those boundaries, but it can be achieved. Another example is like the modifications of the 747 prototype, how it started and how it ended up with. Now, something to think upon, like innovative design occurs when we work beyond the confines of some particular subset of knowledge. So it's like if you ask these questions, is iPhone 8 an innovative design as compared to 7? You can like argue it on the specs front, but for the innovation for like comparing it on this scale, you have to think like what hardwares they have changed, what the progress they have made. So it's like you have to tear the iPhone 7 down, you have to tear 8 down, you have to compare the specs, the battery capacity, the screen size, the processor, yeah, and the taptic engine and all those things. So it's more like just from the specs or just from a look of it, you cannot actually define if this design is an innovative concept or not. Like you have to go into the depth of it. And the second is like, have we reached the optimal capacity in case of internal combustion engines in terms of the performance, like the mileage which you get out of the car? Are we at the brink of like, we are at a stage where we cannot improve it? Are we there or not? So that is like also one more thing to think upon, like basically on the statement that innovative designs occurs when we work beyond the confines of a set of rules which are already defined by someone earlier, like someone who has done the same work earlier. So now we come up to the knowledge-based systems. So the knowledge-based systems is like, take an example of a conventional computer program. So the knowledge about the domain, like since I'm designing a computer program, I need to have this knowledge of where the program is going to be used. Like take an example of a supermarket. I need to have the knowledge of which barcode scanner I'm going to have, which all products the supermarket have, and how the billing pattern is of the supermarket is. Like in some cases, the supermarket, okay, in my personal experience, in some cases the supermarkets provide you with the tax as well, how much tax you paid. In some cases they don't, they just show you the percentage. And in some cases they just provide you with the product-based tax percentage. Like some of the products have a higher tax percentage and some have lower. So in that sense, if I'm a computer programmer, I need to know which products have a higher tax bracket and which products have a lower tax bracket, and how the client or the supermarket wants to like show this details to the consumer so that it's easy for the consumer to understand. So that's how a conventional computer program works. I need to have all these parameters known beforehand, and then only I can proceed to work upon. Then only I can design a system in which would be according to the standards as required by the supermarket. So the operations are predetermined. I don't have anything new in this coming up, like no surprise elements, no like a different barcode scanner, it won't accept. So it's like the confinements are defined already. So it's like the knowledge doesn't exist as an independent entity, but in more cases nowadays, it's like the productivity in designing is increased by automating low-level design decision making. Like in the last discussion, Agatha was discussing about still drawing the on the papers, and okay, I was of the opinion that the CAD systems are better. So it's just an example for you. So if like you draw a certain thing wrong, you have to take the eraser and you have to erase it. What if you just tear the paper? So it's like better in that sense. So you just have a control Z, it's done. So it's just like an example of automating some low level tasks which are not really productive in the design process. So when I say a knowledge based system, what actually I mean? So it's actually a computer program that uses knowledge of the application domain to solve problems in that domain, obtaining essentially the same solutions that a person with experience in the same domain would obtain. So it's basically another fancy statement for a machine learning problem, machine learning or a deep learning problem. So it's like it would include the conventional programs which would solve the like calculate current in a circuit or the forces or tension in a structure, but that won't be actually what this kind of programs would be solving or working upon. So a knowledge-based system is something more than a program which just copies the algorithm used by the expert. It must be able to use it in an intelligent way. So it's like I told the algorithm how I work on these set of examples, and if something fancy comes in, the algorithm should be able to predict, okay, it's not the same thing, it's changed a bit, or this parameter is tweaked, this is tweaked. This does not actually fit in the formula, but like when we are working, our experience comes in. So similarly, the experience of the system should come in, of how the system should handle these kind of systems. So what does a knowledge-based system include? A knowledge-based system may include neural networks, but it doesn't include data mining or knowledge discovery. So data mining or knowledge discovery is not included because it's just available. You don't have to do anything more on it. It's just like a database is available to you. You just have to figure out which features you want from the database. So like a classical view or a programmer's view would be algorithm plus data structure is the program. Sorry, but the KBS view would be the program plus knowledge. So you have the program as well, plus you have the database as well. So that would lead to like a knowledge-based system. So the knowledge-based system embodies a program where goal is to apply the given knowledge. The fundamental characteristic of a knowledge-based system is in the separating knowledge from the application of knowledge. So like this statement might sound a bit confusing, like how do you separate knowledge from the application of knowledge? So it's like I just came up with this. I'm still not sure if it's right or wrong, but I guess it's the best way I could explain it. So if I divide KBS whole system into three parts of the problem data, the inference engine, and the knowledge base. So inference engine is basically a generic algorithm like the machine learning algorithms which you have. The knowledge base is specific to that area of application. So like if you are considering in the autonomous driving or to finding the signal traffic sign classifications, you need to have a big set of traffic signs of the images of traffic symbols, so that you have all the classes available, like the speed limits, the schools, and the pedestrians, and all those things. So since you have to classify it, you have to have a knowledge base of all the different possible test cases or the training cases. So basically what it is, the inference engine is the algorithms which know how to apply knowledge. The knowledge base is the knowledge about the domain. And the program data is the details about a specific problem to be addressed. So why use KBS? So it's easy to implement, maintain. Plus the focus of the developer can be shifted from knowledge towards the independence, can be shifted on knowledge and independence of the program. Although like personally I feel it's not totally independent, but okay, it's fine. We can have it in the discussion session. So like separating knowledge and control. So it's basically you cannot like have knowledge and control in the same thing. You have to separate it for a better performance or a better feature. So what happens is in a KBS system, the knowledge base is different for each domain. But the inference engine, or basically it's the generic algorithm which solves for the same problems. And then the problem data which is like different for different cases. So the control is with the inference engine, but the knowledge is in the knowledge base. So if I change the knowledge base, but I don't have to change the control engine. So the control engine remains the same. It's just the knowledge base which has changed and the problem statement. So it's like I can use the same. So it's like those who have taken machine learning courses. It's more like you have the same algorithms, the machine learning algorithms, but you have the different data sets. So the same algorithm like linear classification, the logistic regression these are the same algorithms, but they can work in the different set of data. So it's like this is what you actually mean by separating knowledge and control. The control is just the algorithm which solves it. The knowledge is like the training and testing data which you're providing. So it can like you can change the knowledge, but you don't have to change the control. So it just saves the time. So by knowledge, I refer to data, information, the rules, the hints, or the clues. And like knowledge sometimes lacks the precision of mathematical formulas. It won't be like a database is going to actually follow a linear line or a curve which can be expressed in mathematical terms. It's more like an approximation. So it's like it's more kind of an approximation rather than accuracy. Yep. So